We have Ramesh come up while we're talking. So that was actually a great segue also for building partnerships. So as things progress through the hubs, you'll hear more about kind of how the hubs can facilitate partnerships as well. So with the academic and industry side. So right now we're going to transition to Ramesh Subramanian. Yes. Gotcha. He's the principal expert at Siemens Energy, and he's led research and development of advanced thermal barrier coatings for gas turbines for the last 15 years. He's currently lead design for additive manufacturing and crowdsourcing approaches to innovation. He's responsible for identifying emerging materials and manufacturing techniques for implementation in power generation product lines, and has over 65 patents to date, and has been awarded Siemens Top Innovator since 2007. So we're going to hear about looking at uncertainty, the impact of uncertainty. We talked about this earlier in the earlier talk on design and manufacturing for advanced materials. So,
hello, good morning, everyone. That was an excellent talk. Kind of got us plugged into the future, and hopefully I can get a push button which says change designer mindset. I would like that, so that I can change it in at least 3 months, so that I can make better products is what's happening in the future. So, so I wanted to just share what we are thinking in terms of as a large industrial conglomerate globally, where we want to utilize advanced materials and manufacturing. And of course, materials uncertainty is one of the key things that drives us from utilizing the full potential of new materials and manufacturing technologies. So my purpose today is to, after having spent several years in developing coatings for gas turbines, which are really important for the efficiency of engines, I still have a lot of lessons learned on how designers still have significant reservations on how to utilize it fully. So the mindset of the guys who make the products is also an important barrier that we need to recognize. And I wish I could tell them, here's your informatics information highway, just plug in your data there or your mind in there, and it's not going to happen that way. So how do we, within that constraint, how do we bring what we are realizing in this multidisciplinary audience of computer science and material science, how do we bring this to those designers so that we can actually make products and make our from an efficiency point of view for us, for example, when we make better efficient engines, we make a safer environment as well. So that's very important for us. And so that's what I'll try to share with you, not very technical, mainly to bring to you the challenge, I guess, or give you a flavor of the challenge that we have in a very very important industry in terms of the energy industry. So, so just to give you a quick overview, first give you a sense, if most of you don't have an idea of what Siemens does, give you an idea of what power and gas division does in Siemens. That's where I'm from. Siemens is so large, you can be from Siemens and not know what the other hand of Siemens or the other brain of Siemens is doing. I will talk a little bit about the advanced materials and manufacturing and how that influences our generation of energy using fossil fuel. And then later on take the example of an emerging technology such as additive manufacturing to highlight the challenges of the things that Bryce and Kevin have already talked about. How do we really bring together process, properties, and performance, and of course deal with uncertainties. The field of additive manufacturing is moving very fast. How will the product implementation of additive manufacturing, will it move just as fast? I don't know. That's part of the challenge, and that's where I'll end basically with the outlook of how high-performance computing and its accessibility to data and analysis can help us utilize it very well. So it's just to spend some time, a little bit, to share what Siemens Power and Gas does. It's a global company, $80 billion going towards $100 billion, and spread globally. And in the US, of course, we have a $20 billion business and more than 70,000 people in the US. And I'm basically in the power and gas division and located in Florida, qualifying for the southeast of the southeast hub as very well from a geographical point of view at least. And we address basically the many divisions or the global needs of energy, mobility, digital factory, healthcare, and financial services. And we are basically located in the power and gas division where we are involved in power generation and services. And we have a corporate group which addresses all of these drivers that we need from a customer point of view. So just to give you an idea, from the point of generating energy from oil and gas and driving it through the different central power generation systems which are currently in place, that's what we are familiar with, and going towards distributed generation with solar and wind, and transmitting the energy, and then bringing it to the industry and the private consumption. So Siemens basically is involved in all of these different sections of energy generation, storage, and deployment. So coming closer to the business that we are involved in, which is in gas turbines, recently with the acquisition of the industrial turbine of Rolls-Royce, or the aeroderivative gas turbines, we have a range of products starting from 5 megawatts up to 400 megawatts of energy that we supply in our industrial gas turbines. And the challenges, of course, are as you cross this range of power across the different engines, the efficiency targets have been continuously increasing. So at some point, these engines, which were now nearly 20 or 30 years old, were in the 30% to 40% efficient engines, and now we are basically in the range of 60 to 65% efficient engines, and the theoretical limit is 70%. So we're coming very close to the point where the efficiency of the engines, especially for fossil fuel generated engines, are getting very high. And therefore, we are pushing the limits of the engines and also pushing the limits, as I'll explain later, in terms of how materials and manufacturing can give you that extra piece towards the end. Because the turbo machinery aspect of it, from the aerodynamics, from the heat transfer, and the structural integrity, the way you make the parts, which have been one of the major drivers of how efficiencies of engines have been increasing, they're almost tapped out. My colleagues in turbo machinery would not believe it, but because I have a materials and manufacturing background and a bias, I think there's a huge potential there. And I'll explain that with a little bit of data that I can share with. So just to give you a reality, going from the size aspect, this is a typical power plant, which you will probably never see in the middle of the city. It's really far away. So, and that's good because of the emissions that it has, and we try to continue to reduce that as well. But just give you a sense of the scale of the buildings that house the gas turbines inside these buildings. And then the scale of the engine itself in terms of how much material and the engineering goes into making these engines. And just to give you a flavor, this is basically the turbine section where most of the hot gas expands out and rotates those rotors, which generates your energy. So this section, the technology of developing gas turbine engines, as you compress the air and you combust it, this is the combustor which will go into these holes, and then the combustion gases then expand and fly out into the exhaust, but they rotate these 4 or 3 stages, depending upon different companies, to generate the energy. And here's where the challenges of high temperature or really the harsh environments of materials, that's the key driver for increasing engine efficiency. So just to give you a cutaway and more, just to highlight some of the areas, the combustion section, which basically starts your flame, is carried down, and then it expands into the turbine section. And there are many areas where the key words are, of course, combustors and transitions, that the flame which carries through into the turbine section is called the transition, where the key focuses are basically to increase spark life and emissions. And in the blades and the vanes, which basically direct the flow, and they turn to make the rotor move, that's basically the key area where the materials and manufacturing aspects come into picture. And this is where the challenges of reducing the cooling air as the temperature of the flame continues to increase becomes very important. And that is a key driver where materials can make a difference. And of course, the leakages that are happening between the stages, the tighter you can make your blade rotate, but you don't have leakages between stages, are the key drivers for increasing efficiency. The more the leakages, no matter how good the different materials are, the leakages will kind of kill your efficiency of the engine. So from a turbine section, this section has the highest contribution to the overall engine efficiency. So how do materials and manufacturing play a role here? So we constantly increase the efficiencies of these engines by playing with materials, changing cooling air, cooling flows, designs. And recently we had a significant amount of brainstorming to say, how do we drive this to our next level, even maybe go beyond 65%. And we did a Pareto chart of what are all the drivers of technologies that can actually make this extra step in technology. And I kind of wanted to, for my own curiosity, and try to lump all of the materials-related topics in the hot section and even some in the compressor section. And I kind of laid out what are all the, how does it stack up? And I was very surprised by the result. Nearly 1/3 of the combined cycle efficiency improvement, more than 1/3, comes from materials and advances and materials and manufacturing advances. There are many turbine-related, the traditional turbo machinery-related activities like turbine aerodynamics, compressor aerodynamics, mass flow, flame temperature, leakages, advances in rotor, how do you exhaust the flow. There's a lot of technical knowledge that goes in there to make the gas turbine. But it was very surprising to note that the materials and manufacturing advances have the biggest impact on the gas turbine in terms of making it more efficient and also low emissions. And this basically, many turbo machinery guys from the designers are now beginning to realize this, and therefore this mindset change is slowly creeping in that, yes, now we really need to make sure that we push the materials to its limit, which means they don't put design margins, which is what they used to do. And if they take away from the design margins, and what's the main thing why they introduce design margins, is the uncertainty of material properties. Why do the materials not perform as well? Is because I don't know how they are processed, how the properties come together, how the product is made. Since I don't know them, the designers don't know it because we are working in our silos. A materials expert, a mechanical engineering expert, and a design expert, they're all very specialized for a reason. But the specialization leads to these individual silos where we don't optimize for design and materials across these multidisciplines. Therefore, this kind of a community where we are actually taking this multidisciplinary approach and kind of mixing it up is very critical, not only in the area of materials, but how can we drive this into design? And that is basically where I will drive towards the outlook, where taking the example of additive manufacturing, there's an excellent example where it kind of flips the model of, I'm going to throw this design over the wall and let the manufacturing guy work on it. Or I'm going to throw the design requirement over the wall and let the materials guy develop these new materials, maybe using some of the fundamental knowledge that the materials guys have. So we have to change that model, which is very important if you really want to use the full potential of what materials and manufacturing can bring to our product line. So therefore, in the next phase, the next set of slides, I'll focus on using this example of additive manufacturing and highlighting how this example brings this need that we are talking about in this big data hub, how does the high computational aspects as well as the informatics, how can it accelerate the development of materials and bringing it into the product line. You'll be pretty surprised how long it takes to bring advanced materials into a gas turbine. Ours don't fly, but the flying ones take longer as well. So let me start with the basic information about additive manufacturing. Most of you may already know this, but just to give you a feeling of the advances and where we are going with regards to integrating design, materials, and manufacturing. So additive manufacturing, in one case of metal additive manufacturing, there are plastics, ceramics, and metals. And for the metal, starting off with the powder, which is atomized, you take the CAD model, in this particular case is a burner nozzle all the way in the combustion chamber that I showed you in the earlier slides. Take an approach where you take a step file, triangulate it, get an STL file, and start scanning them in multiple layers, and you build your support structure, or you orient the part in the bed in a direction which makes it easy to build it by layer. And then this particular CAM file, you of course download it into the machine, and the laser scans across the powder bed, and then the powder basically is traversed across each layer, and the part drops, and you make the part. So you build it layer by layer, and therefore you can make many unique features that you cannot make by any other way, because you can actually combine many materials together. You don't have to join them, and there can be complex shapes that can happen because you're slicing it and building it. And then, of course, you get the finished burner head, which is the design feature that may not have been accessible previously. So this gives you a sense of gives you the sense of the design not being thrown over the wall, because the designer who is currently, if you look at the way we make materials today by casting, drilling, machining, and coating, these are certain mature manufacturing processes that designer sees as, let's just make a drawing and throw it over the wall for the manufacturing guy to go and manufacture it. But here the designer actually has to understand how the design can be sliced up because of the advantages in manufacturing. So the designer has to actually put his thinking cap on to say, how is this manufacturing going to help me design the part different? So therefore, he cannot actually throw the design over the wall, but has to think about the nitty-gritty details of the manufacturing process, the stability of the manufacturing process and the material that's made, so that he can get a better design. So there's an option here now to train the designer, get that push button to change the designer mindset, to start learning and understanding how materials and manufacturing can really help him. So with that in mind, the next few slides are basically highlighting what are the things that we miss that we can help them, what information can we bring to their table, and of course use the opportunity today to talk to some of the people here to learn how we can make it faster. So with this example, of course, many of you have seen many nice pictures of what additive manufacturing can bring to the table in terms of very unique designs. And this is just an eye chart to just give you a feeling of the different features that you can come up with when you start optimizing a certain function of the design to either minimize weight or to change the way the different rotating and stationary parts are engaged together. And there are many consolidation aspects that can happen that gives you a unique approach compared to the traditional manufacturing processes, which can take much longer time and, of course, cannot give you all the flexibility that you need. So the question is, these design features all assume constant material properties. So the topology optimization, which is typically done by the designers and the CAD softwares that are there, they all assume that the material properties are the same. And that is basically one of the key things that needs to change from a mindset. So for example, I just zoomed into one of them where the way you start scanning this in the bed that I showed you before, the microstructure on this ligament is going to be different from the microstructure in that ligament, which means the properties are going to be different. Are we able to get test coupons for every geometry and every ligament in every direction before you design this? Absolutely not. So what do we do in terms of defining? It is not a weight reduction. So for example, if I now push this component in a fatigue, I don't know which ligament is going to fail. So I don't know if this is actually a functional product at all or not. So just to get into the details of what a typical material science guy would see in any of these microstructures, in a simple plane flat buildup of an SLM part, there's a significant amount of microstructure variability. Across the plane, you'll have basically an equiax structure, but built across the 90-degree, which is along the vertical, there is a completely different microstructure. So the anisotropy of the material, depending upon the angle which you build up, is significant. So if you go back to this particular picture, what is the angle in which you're building the part up, and where is the microstructure? We don't know that, and we cannot spend enough time making all those coupons either. So I would never be able to push a design to make new designs without guessing the properties. So how do I guess this with reliability? Well, how am I going to put a handle on the uncertainty, or how am I going to change the designer's mindset to take a risk? So this is basically my main challenge from a company which realizes that advanced materials and manufacturing is important and additive manufacturing is a key enabler. How do I go forward with that? And this also, one of the key things is, of course, utilizing what we already know. We know we can cast parts, and we know the properties of cast material, and we can make debits. And this is where we can take the existing knowledge and apply certain debits to what we already know. And this is one way of doing it, but then how do we apply data analytics so that we can reliably take debits from existing knowledge for new manufacturing processes? Because we wait for all the new manufacturing processes to become reliable and visible for the designer, you're very late from a time to market point of view. So this is very critical regarding the discussions, the presentations that we had in the first two presentations, that we need to address uncertainty. It becomes more important in new manufacturing technologies with higher pressures from the market to bring product very quickly. So if you take the traditional approach, and many of you have seen this, if you start from the process, the structure, and performance, and you get to the product design, what we do typically is on the bottom, where we take a design, take a requirement, define the material function needs, develop a new process or a process or a microstructure, develop the materials data for design. You manufacture and industrialize what you did on the coupons. Now you need to make it for parts and for higher volume. And that is about getting your specifications. What are your qualification and certification approaches to define the product that you want to make in many different vendors, and as well as in a higher volume, so that you can make more of the final product. And of course, that finally leads to a mature manufacturing process, that then finally leads to an advanced deployment, the deployment of the advanced material into the product. So that's nearly a 7 to 10 year turnaround for a full realization from a very low TRL number to up to TRL 8 or 9. And this basically, we have to break this paradigm, otherwise we are not going to fully utilize additive manufacturing in the time where it can have its benefit. So, and when we talk about development, there is also a risk reduction because every component that we make or every engine that we sell has to be insurable. The insurance company has a significant amount of impact on our utility companies before they purchase an engine. And insurability comes from how much new risk are you introducing into the product. So we have to go through steps where we do the element lab testing to system testing, component and large engine testing, so that we can sell a product which has a lower risk. And this essentially this has to happen in parallel in addition to the uncertainty that is introduced in new manufacturing technologies. You cannot do it in sequence. So what is the innovation that we need to address this in parallel? And that is the key challenge that we have to utilize the capability of new manufacturing technologies in our industry, in this specific problem scope that we have from Siemens. So I'll leave this with an outlook. I'll leave the last slide here and then talk a little bit about where, and this will be a topic for discussion during the workshop here as well, is we really need to approach it from an integrated model-based material development. And many of the discussions have already been mentioned, and of course, the MGI initiatives and the ICME initiatives have really accelerated the visibility of such a need. And many of the elements are already in place, but we now have to ask ourselves, how do we drive it into an industry and as well as into the designer mindset and bring visibility so that we can execute on these developments. So let me highlight a few keywords, which are each of them is a separate talk by itself, and there's a lot of technical details available in the literature, and that's not the intent to go into those details at this presentation, but to give you a sense of how we want to address it. So starting from making the process, or when you're making the product in the manufacturing process, the process monitoring, especially in additive manufacturing, you can monitor the process very regularly at a very detailed level. You can get a lot of data from these machines, which we typically have not done for other mature manufacturing processes. So there's a significant amount of data that can monitor real time how the manufactured part is being made. So you don't have to wait until the part is made, cut it up, and then qualify if the part met your microstructure requirement, but can I correlate the process that I'm monitoring, the data that's coming out of the process, to the microstructure or to the defects that are allowable in the part real time. So I can actually, when it comes out of the part, can I take the data that is coming out and understand the correlation of the data to the microstructure? And this really is, this is a huge amount of data that is generated if you assume the volume of parts that are being made. And that is where the big data part comes in, whether you're thermal imaging during additive manufacturing, whether you're looking at the signatures of heat as the part is cooling down. There are many technologies which are already addressing how monitoring can be built in to the manufacturing, into the manufacturing cell, into the SLM cell. The next step is design space exploration. If we want to take the uncertainties that we have in the parts, we don't know where the microstructures are going to be different in each ligament, like I mentioned. How am I going to design parts that will address the varied risk? And you cannot choose one microstructure or one material. If you converge very quickly and decide your material or manufacturing process very quickly, then many things might fail later, and the schedule and cost targets, you'll miss those. So the way to approach it is like your mutual fund. You basically diversify your stock upfront so that if things don't work later on, at least your total mutual funds, the probability of success is higher when you diversify your stock. So it's the same logic. The design space exploration is you bet on low, medium, and high-risk designs that you don't know whether they will work, but if you bet on many different risks, which is your many different design spaces or design choices in your design space exploration, then that will have a higher probability of success later on, that at least one of those designs will make it into your product. And that kind of a mindset is changing the design mindset. And how would the designer change it? We need to give him the materials and manufacturing variability up front to know how the design space can be explored. So this is very critical, and this is the ability of having a tool. Maybe it is an NX tool which has the CAD and CAM, and you build the CAE into it, and you bring the materials topic into the CAE onto the engineering part of it, and that can be done. And that is one of the thoughts that we are thinking from a Siemens point of view. So to bring in the design space and visibility of the design space to the designer early on in the design stages, and enable a screening process from a design point of view. If you can do the heat transfer and structural integrity to know which parts are going to survive in the final product, if you can integrate the tools early on, then this will be very valuable. But it is not an easy topic. It requires a little bit of significant understanding of the workflow, starting from designing to qualification and validation. Next step is basically understanding the heart of a material scientist, which is, let's take a microstructure and see how the microstructure relates to the properties. If we always have to take very simple correlations and address it by polishing the sample or by sectioning the sample, you're going to spend a lot of time trying to understand how these 2D images contribute to a 3D property. So we have to look at a huge amount of data that's available so that we can use new statistical descriptors that enable us to correlate properties to the varied structures. And also from a probabilistic point of view, you need to know how the structures vary so that we build the uncertainty in it. So making our microstructure to property relationships in a mathematical way is very essential if we want to bring the optimization into the design cycle. So materials uncertainty quantification becomes very important, because when you start doing the statistical descriptors, you will understand how to not be deterministic and give a certain specific curve or a design curve, but actually give them a probability distribution. And this becomes very important when it feeds into the design and geometry and the performance requirements, where you'll know that your design is going to have a probability of success, a probability that you will meet the target. And therefore, you can build in the risk upfront. So to do this, to be able to bring process, structure, properties, and performance optimization, this multi-scale optimization, which has the foundations of these have been laid in MGI and ICME, but we have to bring it more real to component design at least in the industry that we are working on. And I believe here is where we can really utilize the hub, the data hub that's coming up, and the high-performance computing to integrate this, because none of this is trivial in terms of integrating the materials informatics and driving it into the design change. So this is essentially the I'll leave this slide and stop here, but essentially this is the way we would imagine, and is a challenge for us as to how we would accelerate materials development and implementation within our product line. Thank you.